Greetings and welcome to a new video about electric circuit problem. This is our second example about the node voltage method. In this video I will discuss the similar circuit we have also discussed in the mesh current method, but then using now a different method, which is then node voltage. Of course, we will look at the calculation step by step and also verify these in SPICE simulations. So let's look at our example. We have this circuit given here and it has one voltage source Vs, 5 resistors R1, R2, R3 and R4, and also the load here. Now we need to use node voltage method to calculate the current through the load resistor RL and also the voltage across each resistor, so 5 of them. Now this is called a Wheatstone bridge. It can be used for measuring, let's say, something which has some string, and that is an application of this circuit. Now the currents here are defined as follows. So the load current goes in this direction from left to right, from this plus and minus sign. The other currents are also defined in this fashion. So I1 and I3 here also shown, and I4, and also the I2 as shown here. So we will use this convention for the currents, the plus and the minus sign, to calculate the unknowns in this example. Okay, now let's go to our solution step by step. The first one is determine nodes. So how many nodes do we have? Now let's again discuss this. This reference node is 0, so that is not a new information. This node all the way on the top, same as this one, assuming of course the wires are perfect 0 ohms. This is also known because that is the Vs, which is 100 volts. So the unknowns here are actually this node and this node. So we can label them, and we have actually now 2 nodes, and that is then label X, another one Y. You can also call them A and B or P and Q. It really doesn't matter, just what you prefer. Now we have now 2 nodes. We can say, okay, write now the Kirchhoff current law for each node. We have 2 nodes, so it means we have 2 KCL equations. KCL at node X. We always start with a very general expression, so without any details. It means actually the following: in point X, the I1 is entering and I2 and IL are leaving. That means the I1 is actually producing these 2 currents. So I1 is producing I2 and IL. That's shown here. So I1 is IL plus I2. For the node Y, I can say I3 and IL is entering the node Y, but I4 is leaving. That means I4 must be produced by these 2 currents, and you can also say that I4 is then IL plus I3. Now taking this together will get you the following information, that I2 plus I4 is equal to I1 plus I3. You can also see it in a different way. Instead of, let's say, setting up these equations, you can say, okay, these 2 currents, I2 and I4, enter this node and then go here, and of course the currents make a loop, and then they again enter this node and then leave here in 2 branches. It means these 2 currents, whatever they are, you add them up here, and they split here again. So that must be the exact same current, of course. So that means I2 plus I4 must be equal to I1 plus I3, exactly what we here have stated. Okay, now let's then look at step 3. Use Ohm's law to express the current equations in terms of voltages and resistors. Now we know the resistors values, but we don't know the voltages. But we have something, of course, in the circuit, which is our source voltage. So that is better instead of using currents, because this equation has a lot of unknowns. So we cannot continue with these equations alone. Now let's then look at the node X again, and then actually use Ohm's law for each current. Just Ohm's law means current is equal to volts divided by the resistor. That's V1 over R1, VL over RL, and V2 over R2. Very straightforward for each current. Now moving on, you can now expand this. You can say, what is V1? V1 is this voltage from this node to that node. That is actually the node voltage here at Vx minus this node at X. That's actually shown here. Of course, divided by R1, you will get your current I1. This voltage, the load voltage is the X minus Y. So the voltage at X minus the voltage at Y is the load voltage. That's actually shown here. And divided by load resistance, you will get IL. Now for V2, that is this one, it is Vx minus 0, which is then 0 is because that is the electric reference point, the ground. So we have Vx over R2. Now we have actually our equation we want. Now we can substitute the values. So we can do directly that. So 100 minus unknown, we need to know that, over 100, because R1 is also 100. And Vx minus Vy, both of them are of course unknown, over 50 for RL, and Vx over R2 is 600. So we have now an equation which has two unknowns. So we need another equation. We will get that from our node Y. Let's also simplify this because the fractions are not really handy to work with. So we can multiply the left and the right hand side of the equation by, I think 600 is the nice value. So it will be then 6 times the numerator here, and then you will get 12 times the numerator here, and then just Vx. So you will get this. Okay, now we need to also make this easier to read, so we can multiply out these parentheses. So you'll get 600 minus 6 Vx, and 12 times Vx, and then minus 12 times Vx plus Vx. That's all shown here. Now we need to have a equation where you have on the left hand side the unknowns, the variables, and the right hand side is just a number. So I want to have Vx and Vy is equal to some number. Now that number is actually 600, and if I now look at it, I can bring actually leave the 600 here and bring minus 6 Vx to the right hand side, and this Vx will be then 13 Vx plus 6 will be 19 Vx minus 12 Vy is equal to 600, and that is actually this, and that's already our first equation. Now doing in a similar form for the node Y. Now node Y has I4, IL and I3. That means just write it down in using Ohm's law, using the voltages and the currents for each the resistance for each resistor. Now V4 is Vy, because Vy minus 0 is Vy, and VL is the same, so we can just copy them from this. And V3 is shown here as Vs minus Vy, just the difference between those two potentials. Now we have this. Now let's substitute the values. Now R3 is known, it's 400, RL is 50, and R4 is 800. Now again, we need to get rid of these fractions. I think let's say the handy way to do that is again 800 here. So 800 left times 800 right, you will get this. So you will get 16 times the numerator of this one. This will just be Vy for the left side. That will be 2 times that one. Now if you work out now the parentheses also again, you will have this one. Now collect now the terms, everything with the Vx and Vy, and then place it on one side, and also with the constant, which is now in this case 200, you will get this. So minus 16 Vx plus 19 Vy is 200, and that will be then our equation number 2. So the set of equations to solve is actually these two. So we need to solve that. So we have two equations, two unknowns. We can solve it, and we get unique answers. Okay, bring it here and let's move on. Now calculate the node voltages Vx and Vy. I just made them blue and red so we can recognize what's happening. Now what can we do here? There are many methods, ways to solve this. I do again what I did in the mesh current analysis method. I just multiply the first and the second equation with a nice number, or what I can find here appropriate, to get one of the variables out of the equation. So I can do 16 times the first equation and 19 times the second equation, so 19. then I can get rid of this Vx. So I multiply this first equation with 16, that will get 304 times Vx minus 192 times Vy, so that's just times 16. And this also times 16, to 600 times 16, you will get this equation. Now this must be then times 19, so you will get this. And now we need to add them up to get rid of this one of the unknowns. Now let's do that. And you will now get 0 times Vx plus 169 times Vy is that 13,400. Now we need to of course get the Vy here, and Vy is then 13,400 over 169. That's approximately 79.29 volts. Okay, now we have one of the unknown node voltages, so we need to go to Vx now. So we can calculate Vx by using one of these equations. I just took this one, so that is this. I know this, so I can calculate Vx. So we can now express Vx in terms of Vy, which is then 600 plus 12 Vy over 19. So we have this equation. And if you now substitute this exact value, you will get 81.66 volts. Okay, now we have also the second node voltage. Now we can move on. Now we can calculate actually what is required in A and also B. Because the current through the load resistor, RL, is its voltage across the two terminals divided by its resistor. So IL is equal to VL over RL, and VL is Vx minus Vy. That's just the potential difference between these two nodes. And RL, of course. And then we have the values we have just determined over RL, and you will get 47.4 milliamps approximately. That's for A. Now for B, we need to calculate the voltage across each resistor. Now let's start with the V1. V1 is Vs minus Vx. Vs is 100 minus 81.66. You will get 18.34 volts. V2, this one is just Vx, because Vx minus 0 is this voltage. That's 81.66. V3, this voltage is Vs, that's point Vs, minus Vy, and we know both of them. So Vs is 100 and Vy is 79.29. You will get 20.71. And V4 is Vy, or Vy minus 0, that's just Vy, and that is also 79.29 volts. The load voltage, again, that's already said, but let's also write it down. That is, in this case, 2.37 volts. So we have now all of the voltages for these 5 resistors, and also the current through the load resistor specifically. Okay, let's bring them together again and then look at the simulation. This is the circuit I have developed in the simulator, and I will show you that shortly in the actual simulator, the Tina TI Spice. And when I run this and generate a table for the DC result, you will get this. What do you see here? Now let's look at the voltages first. I get V1, which is actually this voltage between node 1 and node 2. That's actually shown here, which is 18.34. This one, and that is very close to that one actually, almost exactly the same. V2 here, V underscore R2 is 81.66 approximately, also what we have, very nice. VR3 is 20.71, also what we have, which also is underscore V underscore R4 is 79.29, is also almost exactly the same what we have. And we also VL, which is here, which is 2.367, very close to 2.37, and that's actually what you have here. So those results confirm our calculations also. The current IL is shown here, which is 47.3 approximately, and that's actually also very close to what we have. The node voltages are 2 and 3, and 2 was Vx, which is actually shown here, Vp underscore 2, 81.66 approximately, and node 3 is the Vy, and that is actually shown here, 79.29 volts, also shown here. So you can see all of the calculations are confirmed by our simulations, and it is actually nice to see that they are, let's say, confirming our calculations. Now we jump to the simulator and also show you how you can generate this plot there also, and also I mean the table, and you can see what's happening. So let's jump now to Tina TI simulator. Well, this is a circuit in our simulator in Tina TI Spice. I already prepared the circuit, so we have the VS here, R1, R3, R2 and R4, and also the load RL. Now we wanted to check the current through the load and also the voltage across the resistors. So let's do that, and do that in analysis, DC analysis, and also generate a table. And you'll get this, and you see already the nodes appearing, 2, 3, 1, and also the 0 for reference. Now if I now click on this RL, you can see the highlight of that element. So RL, the current of it, is shown here, 47.3 milliamps approximately, and the voltage across it is 2.37 approximately. So very close to actually what we have calculated, already discussed in the presentation before this. You can also check the node voltage here. So if I go with my pen and then go here, you can see directly this voltage, 81.66 approximately. Or this, you can just click on this one, it will be highlighted. You can also do the other resistors, etc. What you also can do, that will be, I think, nice to see. So let me bring this to the left side, so we have some space here. I think I need to make that connection again. So let me do that. Okay. What you also can do, you can already directly measure actually the voltages here. So I can call this and just, let's say, make that VY. That was VY. And also this one. So let me copy this and then rotate and then make this VX. Now let's also VX. Because when you're only interested in these voltages, let me bring this up. You can also do the following in this simulator. You can say DC analysis and then calculate node voltages. That's it. And you see directly the voltage is there. So it is also nicer to see directly what's happening. You can still click on it. So you can still click on the elements. You can also see the current flow actually. This is the current flow from top to bottom. So that's actually also here. Also nice to see what's happening. And also here, that current is going from left to right. Alright, this is then for the second example about the node voltage method for this DC electric circuit. So we will move on and show you more examples and also other methods like superposition, Thevenin Norton, and many more. If you have any questions, comments about this exercise, please let me know. I will try to answer them as soon as possible. See you next time in another interesting video. Take care.